All right, everyone. Welcome to another episode of the TWiML AI podcast. I am, of course, your host, Sam Charrington. And today I'm joined by Jilei Hou. Jilei is a VP of Engineering at Qualcomm Technologies. Before we get into today's conversation, be sure to take a moment to head over to Spotify, Apple Podcasts, or your listening platform of choice. And if you enjoy the show, please leave us a 5-star rating and review. Jilei, welcome to the podcast.
Hey Sam, very nice to meet you here.
Yeah, I'm super excited to dig into our conversation. We'll be talking about, a pretty broad variety of things because you cover a broad variety of areas, but we'll be particularly digging into the work that you and your team are doing around generative AI on devices. But before we jump into that topic, I'd love to have you share a little bit about your background.
Actually, my own myself by training, I'm specialized in information theory and signal processing. So this is about 20 years ago when I obtained my PhD degree from USSD, and then I came to Qualcomm right afterwards. So one thing I should remember to note is the founding father of the information theory, whose name is Klaus Shannon. He happened to be one of the early pioneer in the area of machine learning too. And also many of the machine learning, modern machine learning practice and achievements actually are inspired by information theory. I'll give you one example. Many times people using a term called a KL divergence, which is a divergence between two probability distributions. Actually, that concept first came through in the area of information theory, was introducing that context. And then later on, it's become a very, very popularly used when people using the training objective when they're trying to training neural networks, for example.
So there's a kind of a match made in heaven, so to speak, between information theory and artificial intelligence.
Yeah, clearly. Yeah.
And that's particularly the case at Qualcomm because a lot of what you do from an AI perspective is focused on applying machine learning algorithms to compression, which is also kind of a natural place for information theory.
Right, right, right.
I'm curious. I've spoken to many researchers there at Qualcomm, but you've had an opportunity to be instrumental in the kind of forming and development of Qualcomm's AI research group there. Can you tell us a little bit about that experience?
A few years ago, we made a few acquisition of the AI startups, and from where we assembled a few very smart kind of minds people in the machine learning area, and many of which actually are very influential in a machine learning research community. So then, when we assemble this talent team together, and it's become natural. This is around 2018, and we're starting this is initiative called a Qualcomm AI Research. The key, right, is about to drive and accelerating the cutting edge research to helping Qualcomm to accelerate the machine learning, adoption at at a company, as well as contributing back to the research community as a whole. Maybe, yeah, adding to this, very early on, we have a very clear focus in terms of our research agenda, primarily focused on the power efficiency for on-device AI experience, and also think about personalization. So when we think about power efficiency, is largely think about bring machine learning workloads to the device where we can run very efficiently and with a very good user experience. And personalization is more coming down to the idea of make sure the machine learning models can be adapted to your personal need and a personal preference. For example, a lot of the speech, and audio use cases fall in that category. And I have to say, with all the earliest research we have done, one of the clear highlights we have achieved is we have building the world-class um, quantization research team. So quantization research team is primarily boils down to if people today, right, you're using FP32, FP16, or even people can talk about FP8, but I think we'll be able to quantize them into more uniform kind of data grids, so where the data can be presented much more efficiently, and also even from a computation, from an implementation point of view, it will be the most power efficient data format we can implement on the device. I later on, as we're touching on more the topic around generative AI, we'll be able to say a lot of breakthrough in terms of the ability we are able to bring all these use cases to the device. Actually, quantization play a very essential role for us. Yeah. Lately, I think we have expanded our team. I think Qualcomm AI Research we probably have size between 200 to 300 people in our range. So we cover very broadly in terms of when you think about fundamental research, when you think about platform research largely alluding to bring all the efficiency technique to our AI compute platforms. And also is it coming down to applied use cases where you think about a lot of vision use case, even a lot of wireless use cases. We can bring state of art solution to all the different technology and verticals.
Hmm. Hmm. And so, generative AI is certainly a bit of a buzzword nowadays. Is that a new area of research for Qualcomm AI research, or is it something that you've been working on for a while?
In general, I would say, uh, when people talk about generative AI, right? I think it's a subclass of AI where you're able to generate or even regenerate new content. The new content can be text, can be image, can be video, via resampling, or sometimes it's called a reconstruction too. So the even though the term of a generative AI is a bit new, but the technology behind it, what people call it generative modeling, actually has been around for quite many years. For example, the familiar terms people think about, GAN, think about VAE, think about autoregressive models. Those, technology or kind of, machine learning practice has been around a few years now. So, but one of the why generative AI just all of a sudden becomes so popular, in a little sloppy way to explain, right? Is really boils down to people realize actually just with the same kind of a generative methods, but if you are able to feeding this model very efficiently with the internet scale data, where you can just scrape the data from the internet, think about text data, think about image or even video data, and then being able to feeding the model through, and also allow them also have a massive capacity to absorb all the data in a sort of a very knowledgeable way. I think that's a situation, so we're sort of where the breakthroughs are happening, and then generative AI just bring a lot of disruptive benefits to the consumer and also to the enterprise and industry altogether. Yeah. So uh, one thing maybe I can add into this is, as I mentioned, when we think about generative AI, I think in a more broader term, I think our research group has been working in these areas for quite a few years. So one of the key area we have made a lot of investment, actually is a topic called data compression. So when you think about data compression, you can think about the terms of speech compression, think about image compression, or think about video compression. So, one thing early on when we made an investment in this area is because if you think about today, right, the data traffic on the internet today easily can be 80-90% are all coming from an image and a video itself. So if we're able to using AI approach to further improve the compression efficiency of the image and a video, I think this is going to providing tremendous value to Qualcomm and also to the industry as a whole. So I remember this is like probably 4 years ago. We have a jump into this, and one of the early thought was saying, "Hey, look, this is essential. You think about you have a sender, you have a receiver, right? Transmitter and receiver, and it's about on the transmitter side you have." Actually, in this case, in general, we are applying this very popular technique called a VAE. It's called a variational autoencoder. So you have on the transmitter side, you have an encoder, right, which is trying to compress all the pixels down to latents. which is in a much more compact space. And then on the decoder side, then you will be able to decompress and reconstruct the samples. So in that sense, you can think about the decoder essentially play a very popular role as what we're discussing today. From a latent, you can reconstruct or resample to regenerating, the image or video samples. So the bottom line in terms of you think about the concept, in terms of the practice, is very similar how the diffusion model is running the denoising step in terms of give you the reconstruction of the samples when you think about another use case of a stable diffusion. So this is back in 2019, and also I believe our team back then, 2019, in the ICCV 2019, one of the premium conference in the machine learning, we have published one of the uh, uh, early papers in terms of applying the deep learning end-to-end approach towards video compression. Actually, that paper getting very high citation as is a very popular among the research community. Yeah. So then, soon afterwards, we're looking at a variety technique and how to improve and how to adding new benefits to this. Uh, as we speak today, I would say we are able to improve the efficiency to the level it's probably at least on par or even slightly better compared to some other conventional technique. But more importantly, I think this kind of technique is bearing a lot of utility and flexibility. For example, one of the things we have invented new technique is about think about a video stream, right? It could be your social media video, or it could be just a, let's say, a recorded film, coming from Netflix, for example. If you're able to apply the neural net based approach, then essentially you're able to customize, even personalize the content in terms of the codec itself to make sure the codec can be specific, customized to the video itself. So in essence, we are able to achieve even better efficiency and also make sure the compression is done in a way even customized to the video scene itself. So a lot of potential. And also, we are the first one to bring this kind of AI-driven video compression concept to our device, to our mobile device. I think remember this is about a year ago. We are able to demonstrate a CVPR last year on the HD quality, the end-to-end AI and driven video compression scheme. So this is getting a lot of a positive feedback from a research community as well.
It's an interesting analogy that you draw between generative AI and the diffusion model, stable diffusion in particular, and compression. You can almost imagine thinking about, what if some compression model where you've got your transmitter and you convert that into text, and text is easily compressible, and then you use that text to generate a new image. If you can do that perfectly, that would be a great compression scheme.
I think that's why the a lot of research opportunity in the AI area is endless for us. A lot of cool opportunity ahead of us too. So yeah.
So let's talk a little bit more about stable diffusion and the work there. You spend some time working to get stable diffusion running on a device. Why is that important?
One thing we feel motivate us a lot in terms of running stable diffusion and on the edge, coming down two folds. On one side, stable diffusion model itself, right, is an open source model. So that's why it's very, very popular. And being able to putting effort into stable diffusion and also contributing back to the whole AI community, we felt this is a really big thing. We can help altogether. So on top of which, I would truly feel bring stable diffusion to the edge to the device. There's quite a few benefits I can elaborate here. Now, first of all, right, it's really coming down to privacy. Privacy coming down to, for example, if I have a personalized prompts, which I probably hesitant to share to the cloud. But in this case, if we're able to keep the stable diffusion all running all together, right, in a device, so my prompt and my content all strictly speaking stay on the edge, I think this is a highly, highly sort of beneficiary from a consumer point of view. But then it's also coming down to cost. For example, we know when we discuss and communicate with all the hyperscaler, all the cloud players, they did express a lot of concern. This kind of large, massive model running from the cloud point of view, in terms on the per inference, or in terms of when you think about running millions or even billions of inquiry, for such kind of use cases, the cost just become prohibitive from the cloud players' point of view. So in this way, we are kind of distributed, right, and also getting on all the devices, a billion devices, to amortize the inference cost. This is a huge benefit to everyone in the AI ecosystem. So, and also lastly, we also feel from even reliability point of view, from a performance, because you don't have to send in the cloud. Sometimes the cloud can run out of capacity, but then on my device, I always have the capacity, always ready to process my personal needs. Yeah, so I think we see very exciting. We bring a lot of value in terms of bringing stable diffusion to the edge. Very cool to see that happening, and I get a lot of positive feedback here.
And so, from a research and engineering perspective, what were the key challenges in making that happen and getting it to run on a device?
So we can share a few insights about this question. First of all, we'll see the challenge it clearly is coming down to model size. So before stable diffusion, the typical machine learning workloads, deep learning workloads we're running on the device, it's a more or less, let's say, less than 100 million parameters. So stable diffusion alone is like 1.1 billion parameters. Is almost like 10 times, right, in terms of workloads. And additionally, on top, you remember the stable diffusion, you need to running through the denoising steps. In the default stage, you don't have to running through, let's say, 20, 50 steps. That's all kind of adding up in terms of complexity and the challenge, how to being able to running this workload on our device. So one of the first question is to handle this kind of workload in terms of the robustness, and also the automation we have to make sure maintain to letting this model can run through our AI software toolchain. This is a really good challenge. It's a really good stretch, but it turns out our software stack is pretty robust to handle this. At the end of the day, and we're very happy to see that. The second challenge clearly coming down to the inference latency. This would require a full stack research and optimization. Make sure from a model, system algorithms for to software stack, and eventually to the hardware silicon processor itself. End to end, we have to look at everything to be working very nicely together. So, among which I would say, as I mentioned earlier, I think one of the big recipe we are being able to throw into this is about a quantization research, because I think the model I remember when it came out is like FP30 to FP16. If you just run them natively, even assume the model size you can support, this is clearly going to take even more than a minute and being able to run it on a device. So then probably user wouldn't be able to have the patience, right, to wait that long to say, hey, what is my final image coming out after a minute or two. So then, what we've been able to do is without retraining the model, simply by applying the post-training techniques, and we are able to quantize a model efficiently. In particular, on the weights, we are able to quantize to 8-bit weights. But then we realize that simply if you just do a simple naive post-training quantization, we realize that the signal to noise ratio, or in terms of quality of the pixel you generated, actually is not good enough. So from that point of view, we realize we have to apply more advanced PTQ, post-training quantization techniques. What's something we call add around. So add around in a simple way you can think about, intuitively speaking. Most of the simple way, every single weight, when we think about quantization, usually we're just trying to quantize to the nearest neighbor individually. But the add-on essentially, instead of looking at each of the weights individually, trying to creating the quantization more across the board in terms of per channel, even per tensor basis. So this will give us a more holistic view in terms of all the weights when you're going up and down. There's a more systematic way to think about on a bigger picture. What would be the better way to apply rather than applying on a single weights? So it turns out the add around, in general speaking, we realize if we think about quantization, right, to 8 bits, for example. So add around actually magically can giving us virtually, it's still 8 bits, right? But just because of applying the add around technique, we're able to add in probably one more bit. But this one more bit is magical because a one more bit, even virtually, roughly speaking, if people understand, the term of signal to noise ratio, is adding us about 4 to 6 more dB. So 4 to 6 dB is very crucial in terms of able allow us to getting very efficient data format without retrain a model altogether. So that's why we are able to very quickly, within very short time, applying the add-on technique, and I'm able to release a demo at an MWC event, back in late February timeline.
Yeah. So just to recap, there, the two key challenges were, one, being able to work with this large model using your existing kind of tool chain and workflows, and then the second is um, some more specific challenges that arose in trying to achieve the desired performance levels, and uh, in particular the use of quantization. Um, Maybe I think this question is related to both of those challenges. Did the ultimate solution from a quantization perspective, was this kind of an out of the box, you know, push button, application of the tool chain, or was there a degree of research effort involved in achieving the result?
So this is a really good point. We actually created an open source toolkit. It's called AIMET, called AI Model Efficiency Toolkit. So the intent of which is trying to democratize and providing very easy to use quantization toolkits for average, let's say, data scientists, or can be ML engineers, being able to using with the convenience and ease. So from that point of view, for example, let's say take the post training quantization as the example. We have more turnkey flavored quantization features is available in AIMET. Actually, for example, developers can just pick up and use in a very relatively easy kind of format. But on the other hand, I have to say, Adderall is a bit more advanced technique. You have to apply essentially like a localized optimization procedure to all these models. But of course, we are packaging this localized optimization procedure into the quantization flow itself. Sort of letting things easy to do. But on the other hand, I have to say, because it's still involved as a local optimization procedure, it still takes some time and being able to run through the optimization procedure itself. So actually, one of the very essential effort we're trying to working on is when we trying to apply these kind of advanced technique to large or even massive models, we're trying to reduce the optimization time significantly. So actually, in essence, we're trying to bring more efficiency to this kind of advanced technique, and hopefully they will show up in the AIMET very very soon as well. So.
Got it. So this required the local optimization is beyond the current capabilities of the toolkit, but maybe something that can be generalized and rolled into the toolkit for future use cases.
Exactly, exactly.
You know, I'm wondering if you can elaborate on that a little bit, and how specific to the diffusion model the local optimization that you had to do was, or conversely, how generalizable do you expect it to be, or what aspects do you expect to generalize?
Let me say the following. For example, Adaron, we when we apply to the stable diffusion models, I cannot get into too much details, but I can talk about a high level. We probably take about hours running time to apply the Adaron optimization procedures. But our goal actually, we are probably within line of sight. We are targeting to reduce this optimization time from hours to minutes. So, and hopefully with this application of more advanced version of Adderall, and we'll be able to make sure it's become more turnkey, right? Bring more benefits to all the developers. So yeah.
I don't think you actually mentioned the results that you arrived at with Stable Diffusion. You were able to get that down to 15 seconds or so. Is that right?
We're able to getting down to less than 15 seconds. It's I think our record is like around 13 seconds right now. But on the other hand, um, without going into details, we are actually working on the even more efficient version. When we think about um, all the efficiency technique we can put around. Uh, I think we are very hopeful we can, bring this down to less than 5 seconds. Hopefully, in the next few months, we'll be very happy to report back to Sam, by then. So yeah.
And without going into those details, are you expecting it to be in the same domain, additional work on quantization, or are there new techniques that you're looking to apply?
We look at a combination of different kind of techniques here. So quantization is still part of it too. So
Got it. And to what degree do the challenges that you saw in working with Stable Diffusion and getting that to run efficiently on device apply to other types of generative AI models like large language models?
this is a really good point. So in general, actually, the one of the nature of a generative AI, right? As I mentioned earlier, because essentially is a training on internet scale data. So one of the sort of a property of these models, they have to be really large and being able to absorb all the knowledge coming from the internet scale data. So uh, and then in this space, actually, I can divide this kind of generate AI model largely to two different categories. We call LLM, right? Large language model. The other category I call LVM. It's called language vision models. So you can think about the diffusion model is a largely stay under stable diffusion, right? Stay under the LVM in that category. So within that category, I would say a lot of the technique when we're looking at it from a quantization, from a software compilation, from a system hardware software co-design point of view, the practice we're doing from a stable diffusion is very very directly leverageable apply into all the other kind of LVM models. For example, if you have heard about there's a one very popular model lately just come out called sam. Actually, it's happened to be with your own name. It's called segment anything coming from Facebook. So, very early preliminary results, we realized, technique we're doing for stable diffusion is very directly applicable to the same model coming from, Facebook. So then the LLM model is somewhat different. Somewhat different in a sense. LVM model, the most computation, and when we think about signal to noise ratio, when we think about the quality of the regeneration, is you have to going back to the pixel space, right? So that's why there's a more clear analogy between stable diffusion with all the other LVM models. But coming back to LLM model, it's all kind of a, or I should say, largely is a text to text. So when you think about text to text, is a more in abstraction form. You think about it's a, from a token to token. So it turns out the signal to noise ratio, when you think about the noise handling, when you think about the regeneration of the token itself, it's a very different kind of a beast as compared to LVM. But still, with that said,
Why is it so different? You know, we think about these things as all being vectors, you know, representation at some point.
so very different in the sense of vision model, the vision model, because eventually at a pixel level, I need to having that representation in terms of grayscale and also RGB colors. So in essence, those will have a demanding eventually final the pixel output. I need to having enough bit width to represent. But if it's coming down just a simple text, and then the bit width, I can be a lot more aggressive towards in terms of compression, in terms of quantization. So in that sense, for example, a very popular data format when we think about the stable diffusion, what we came up in, for the MWC demo, right? That's just like 8-bit for weights and 16-bit for activation. But for the LLM model, because it's a more abstraction form of, you think about language tokens, language symbols, actually we can compress much more aggressively down to 4 bits. And even though we have a very early stage, we believe we have a potential maybe further reduce even beyond 4 bits. So I'm just saying, LLM in general speaking, because on one side, I think this is clearly benefits to us. Because on one side, we felt there's a more value to bring smaller bit width to LLM compared to Stable Diffusion or other LVM models. But on the other hand, generally speaking, right, you think about LVM typically is in a range of the model size between 1 to 5 billion. But when we go to LLM, right? If you think about cloud version, like more than 100 billion parameters. But even on the edge model, the very popular Llama model from Facebook, they're starting from 7 billion too. So what I'm saying is, the clearly the quantization to smaller bit would have a more incentive to enable us to bring all these large language models to the device. So I think this is where actually we believe one of the very important area we have to make sure stay ahead of the curve. Eventually can bring the value to the industry, and also make sure we're on frontier to bring all these large language models to the device. Actually, we believe at this point, we are very confident we'll be able to do so, and we probably look in the second half of the year as we working across the board between research, engineering, and product team. We're going to bring a lot of new announcement to the industry.
So just to make sure I got that, I think my takeaway from that last bit of your explanation is that both the LLMs and the LVMs are challenging to run on device, but for different reasons. For the LVM, it's because essentially your feature dimensionality is so high with the pixel representation. On the LLM side, it's the size of the model, owing to the size of the training data.
Right, right, right. The other thing is, again, just kind of sharing with you, and also the insight we have obtained looking at both LVM and LLM, right? So, um, on one side, this attention module is a very sort of a important, kind of, you know, constituent block, right? In terms of underneath the hook and being able to support both LVM and LLMs. So in that sense, being able to putting out the best computation support, from our AI compute platform for softmax for attention module, we believe we in a best spot, at least from the edge, from the device front. But on the other hand, we also realize the computation nature between LVM versus LLM is also very different, meaning the compute density for the LVM is potentially much higher on a per weight basis as compared LLM. This is also driving very different requirement when we think about this the software stack. When we think about the graph level compilation technique, applying to LLVM and LLM somewhat can be different too. So, but on the other hand, we have also very good recipe when we think about automated version of a software compilation, from both the algorithm and also from a software practice point of view. We are very confident. We can push on both frontier and putting the most efficient form of implementation of the both category to the device. In very very near term for us. So
Yeah, it's tempting to think that since transformers are becoming this kind of unifying architecture across all different modalities, that you would just have one problem to solve. But it sounds like you still have very distinct problems to solve for each of these new models that you want to bring to the device.
or another way, because maybe we can just open up a little bit. It's also sort of coming down to term how people have the vision in terms of for the future, where AI is evolving, right? And also how is it growing, how things are going to be look like. In a way, many time when I'm talking to a lot of researchers from my team, one of the popular view, I believe this is probably resonate with a lot of advanced research group across the world, is coming down to, if you think about you know largely in the form of a GPT or LLM model itself, it's like a probabilistic processing engine that on itself, when you think about doing things like language processing, when you think about reasoning, when you think about planning, this kind of more abstract form of advanced cognitive tasks, I think those things still become going to be constructed largely in the token space. Just like human today, when we do say 1 plus 2 equal to 3, largely back in your head, you are running through this thing in a symbolic way in your head in a certain form. But on the other hand, you're gonna have eyes and ears, you have arms and legs. Those are need to more interact with the real world, where you have to dealing with the world from a pixel space. And those are the things going to be more involving the model like LVM and a pixel processing. So that's why you're still going to see things stay within LLM or GPT processing, going to be more abstraction form. But things going to, as I said, eyes and ears and arms, legs will getting more involved in pixel, more intense, computation. So in that sense, so
To what degree does that observation kind of suggest that um, multimodality types of models that pull in both of these is an area that needs to be focused on from a research perspective for you?
so on one side, actually, you know, we see a very strong need, right? Even just from LLM processing itself, you think about ChatGPT, right? Today, if I'm sitting next to a PC, I'm sitting on the next terminal. It's sort of a natural. I can do, keyboard, right? I can do, text prompt, and I'll getting the text back from the ChatGPT. If I'm using ChatGPT or something equivalent as my, let's say, in the use case of a personal assistant on my mobile phone, I'm carry my mobile phone around. I want to communicate with my personal assistant, right? It will be a bit cumbersome. I have to type all the time. So in essence, if I can take the my hands away, right, become hands free, even touch free, I can essentially going through using speech as modality to communicate and exchange with the chat GPT. That itself, I think already we felt a strong needs and probably is already some of the people are hacking and make that happen, and then we're assuming this is going to be really popular as a way people are going to communicate with GPT. But adding on top, I think from a research side, actually this is a topic we started about 18 months ago. We're starting a research track in our Qualcomm AI research. It's called a System 2 research track, because I think this is a term coming from Joshua Banjo. He talked about system one, right? Is more as a way of you do pattern recognition, is a very instinctive, right? And you're just kind of trying to do a pattern recognition in a sense. But the system two is a more cognitive. It's more think about reasoning, more think about decision making, and they're going to be processing a bit to kind of slow down kind of format, allow the machine to kind of reflect and also make more sort of high level cognition in a sense. So from a system two, I think one of the strong flavor we're trying to bring into the space essentially is trying to bring visual or vision modality into LLM. So in a way, think about you can be running a visual prompting, right? In a visual prompting, whenever the camera is seeing the real scene, and it can have a scene understanding, and can sending the process token after visual understanding into LLM, and LLM can take this visual inputs and be able to communicate and discuss with let's say human or other people, right, in a more sort of cognitive way, taking all the contextual sort of environment into account. I think this will bring a lot of more benefits altogether. By the way, just on this topic, in terms of visual understanding, visual reasoning, there's a very challenge in kind of benchmark laying around. We have most recently have made some breakthrough in this area, and we make this one submission to NeurIPS. I believe our researcher has published state of our results. Essentially, probably become on top of the leaderboard for some of the benchmarks. So very excited to see a lot of progress in this space. So
Maybe jumping back to your perspective, kind of leading this research organization. I'm curious, does the if we can say the rise of generative AI, although we've talked about that and how it's not necessarily all new. Uh, does it call for dramatic changes in priorities or organization or anything like that from your perspective, or from your seat, is it another area to explore, like all the others, and to kind of tie into the various things you're doing? How do you process everything that's happening out in the world with regards to generative AI, and kind of direct the organization there?
So that's a really good point. On one side, I would say, things are not related to generative AI. For example, a lot of work still in a classification, prediction, kind of planning kind of space, not using generative AI technique. I think a lot of the things I think still have its own value, and also in terms of our technology investment and working with all different kind of BUs, verticals, I think there's still a clear impact. I think we're not going to stop in those. I think those are still something we're going to continue our strong investment. But having said that, I think generative AI itself, in terms of the sheer volume of the research breakthrough and also the business impact bring to the corporation, to the enterprise, to the industry, right? It's just humongous. So from that point of view, we definitely is very seriously looking at how to uh, readjust our research organization, make sure that all the R&D effort we can organize around the LLM and the generative AI and can allow us to bring the best value to the company and to the industry. So a few things I probably can mention just at a very high level. From generative AI, we feel we're going to lead the industry and also contributing very substantially. So the first thing, I don't know if you have heard, is running the generative AI models actually is very inefficient. When I say very inefficient, if you imagine the ChatGPT model is building on top of the model size of 175 billion parameters. So the 175 billion parameters actually turn out the inference model is you cycling through all the 175 billion parameters in terms of all the data transfer from a memory to the processor and running through the computation inside the processor. You only generating one output token at a time. So that itself is extremely inefficient. I think a lot of researcher and a lot of company realize. So one thing we felt we're going to bring to the table here uh, is looking at going beyond a single token generation. How can we bring multi-token generation to the table? So then we can substantially reduce the bandwidth consumption and then make sure we can improve the compute density and also make sure we can reduce the inference cost from both cloud and edge side in a very substantial form. So that itself, we felt is a very important topic, even from a overall economy point of view. I feel we can bring a lot of to the table. The second thing is about also about training of all these models. This is still very early stage, but we just felt training all these large language model today in this compute paradigm today, training everything on a super expensive NVIDIA, DGX SuperPod. I think that itself is overkill. So we're looking at bringing a lot of sophisticated optimization and mathematical algorithm, really trying to looking at a simplify the training of these massive models. So in essence, we felt there's a lot of good hopes we probably can bring table there too. The last thing I like to mention is also a new AI inference paradigm, what we call the hybrid AI. So when we think about hybrid AI, essentially is a new mechanism where we can allow the edge and the cloud to working very efficient together. So in essence, you can think about one of the popular kind of paradigm in the future will be if we can equip right the edge device with large language model capability, where we can run substantial amount of these LLM workloads on the edge and only on a needed basis. For example, could be challenging, could be sophisticated use cases. On an occasion basis, we can offloading all the compute back to the cloud, but then to make that kind of vision happen, to design the system architecture to make sure bring the LLM capability to the edge, and also having the ability to sort of direct the workloads dynamically between the edge and the cloud. I think Qualcomm also, I feel we are in a very prominent position. We can work with all the cloud players to make this vision to become a reality. So overall, we felt there's a lot of we can contribute in the LLM area from both a research and a business impact point of view. We are definitely very much looking up to a lot of new opportunity in this area. So
Well, Jilei, thank you so much for sharing with us a bit about all the things you're up to there in making these technologies accessible on our devices.
yeah, thank you, Sam. Really appreciate it. I'm very happy to talk to you here.
Same, thank you.